Hola, welcome to my talk on XPC and a bug named Rootpipe. So as was mentioned, my name is Patrick Wardle. I have worked at a bunch of acronymed places, including everyone's favorite place, the NSA. Currently, I am the Director of Research at Synack. So Synack does crowdsourced vulnerability discovery with vetted security researchers. Pretty much anyone can sign up and get paid to find bugs. It's kind of cool. It's a freelance opportunity. Once you sign up and get vetted, you don't have a boss. You can connect in and hack on our customers' web apps, mobile apps, IoT devices, and even network endpoints. And any acceptable bugs you find, we actually pay out. Now, I don't see any of our customers here, so I'll let you in on a little secret, not so secret, I guess, is that their security is really poor. It really sucks, so we end up paying out a lot of money. So I briefly want to talk a little bit more about our red team, which are our external researchers, our freelancers. So as I mentioned, anyone can sign up. There's a few tests that you have to pass, but this is really just to validate your skills and vet your experience. And then you can start finding bugs at your own time, any free time. Again, no boss, nothing like that. And why choose Synack? Well, there's a few good reasons. So first, we have a smaller crowd, right? So some of our other competitors maybe have tens, 20s of thousands of researchers that you're all competing against. And if you find a bug and someone else has found that too, they're going to get the money. Synack, we're a lot smaller, so it's more likely that you're competing against fewer people. We also have bigger companies, bigger customers. So a lot of banks, Fortune 500 companies, healthcare, credit card companies. So this means the bugs you find are going to get paid out a lot higher. So our average payout is now approaching about $1,000 USD. And actually, we just had our first external researcher, our first freelancer, cross the $100,000 mark. So again, lots of money to be made. Lots of money that we pay out because, unfortunately, our customer security is really very poor. So you can either check out synack.com or stop by our booth to sign up. All right, so what is today's talk going to cover? We're going to start with an overview of XPC, which is a modern IPC mechanism on OS X. Then we're going to talk about a privilege escalation bug that was named Rootpipe. Following that, we're going to talk about and examine some malware that actually exploited this vulnerability before the public disclosure of it, meaning it exploited it as a zero-day. Then we're going to talk about Apple's patch and where they thought they sealed the hole, and then how I was able to sidestep Apple's patch and bypass it completely. And then ultimately, the second patch Apple released, we'll look at what they did, which I think closed the hole, at least for now. All right, so usually credits are given at the end of a talk, but I wanted to do this first because there are some people who were very instrumental in this research. So Ian Beer, he works at Google Project Zero. He's done a lot of really good talks about low-level XPC and found a lot of low-level XPC bugs. So as I go through this talk, if you want more details about the low-level internals of XPC, I'd recommend checking out some of his slides. Next person is Emil, and I can't pronounce his last name, so I'm not going to try. He was actually the one that publicly disclosed Rootpipe, so he should get a lot of credit. And then Pedro was the one that did some initial analysis of Apple's patch. He didn't find any, or didn't point out any flaws, but it was instrumental in helping me figure out the flaw where I was able to bypass their patch completely. And then finally, I always like to mention the Mac OS X and iOS internals book written by J11. Second version is about to come out in a few months. If you're interested in learning more about OS X and internals of the operating system, I would definitely recommend checking out this book. All right, so as I mentioned in the overview, I want to start with an overview, an intro to XPC, which is a modern IPC, inter-process communication mechanism on OS X. Since Rootpipe is an XPC-related bug, it makes sense to really understand how XPC works, kind of peek under the hood and understand exactly what's going on. So XPC, as I mentioned, is an IPC mechanism with two goals: privilege separation and stability or fault tolerance. Basically, when you XPC something, you can break it into separate components. And these are going to be individual processes. So this allows each XPC component, which is its own separate process, to have its own sandbox. So from a security point of view, this provides a lot of privilege separation, because what you can do is now you can assign certain sandbox policies to each XPC component. And we'll see an example of exactly how we can do this. Also, in terms of stability or fault tolerance, again, since the components have now been broken out into separate processes, if any of them crashes, that won't affect the main application. So instead of taking down the application entirely, the application can just, for example, show the user a message saying, hey, sorry, this component crashed, but the operating system can automatically restart that XPC component. So again, definitely makes sense to kind of break these out. So XPC is used extensively by Apple in OS X in both frameworks and applications. So if we look at the slide, we can see a list of frameworks, address book, WebKit. And again, this makes sense to put separate components into separate processes for both security and stability point of views. So think about WebKit, right? It does a lot of rendering, it hosts plugins. Again, if this was all in one process, if any of those components have had a vulnerability, and we've seen a lot of WebKit bugs, if an attacker got arbitrary code execution, they would be running within the context of the browser, which is a pretty powerful place to be. Now, if we break these into separate components and really sandbox them tightly, if an attacker finds a WebKit bug, they're still going to be running now in a highly constrained environment. So they're going to have to find a sandbox breakout. So again, just another layer of security there. If we look at the applications, we can see apps such as Xcode and iPhoto. Again, Apple has taken components, for example, rendering and converters, which are often error-prone or crash, and put those, again, in separate XPC components. Again, this means if those crash, they're not going to affect the main application. iPhoto can say, hey, I was unable to process that image, show a nice pop-up to the user, but it's not going to take down iPhoto. And again, if an attacker finds a way to exploit a vulnerability in iPhoto, for example, in a rendering component, again, this is going to be in a tightly sandboxed environment. So I want to kind of go through a detailed example. Did we lose the screen? Yes, it's black. It's still showing up on my laptop. I can turn my laptop around. No, I'm just kidding. Okay. I would dance, but I'm really bad at dancing, so. Well, I can keep talking a little bit about this, and then when the slides show up, we can go. So I mentioned, I'm going to kind of show an example of how we can take an example or sample application and then break it out into XPC components. So the example I like to use is an application that does three things. And again, this is just an example. Downloads, unzips, and displays images. So you can think of an application that talks to the internet and downloads albums of pictures and then extracts those and parses those. So if I would have written this application a few years ago, I would have just had one application that did all three of these things. It would download, unzip, and display that all in one process. This would be problematic if there was a vulnerability in any of my code because this would impact the main application. What I can do, though, is, yes.
Did you check anything on the resolution?
I didn't change anything, no. Maybe it's the NSA. They're everywhere. Can I unplug this?
Okay, put it out.
Okay. Damn it, Apple. You're supposed to just work. This is what I get for talking smack about Apple. They finally got me. Oh, nice. I hope these are both for me.
Bueno, conéctenlo directo.
Yeah, there we go. Worst case, I can just run through it with this. Cheers. Thank you. Gracias. Yeah, you want to try hitting play again?
Play.
Play.
Sí, no, pero el play no,
Yeah.
se pone todo negro el play.
Yeah. We can just run it through this. This is fine. Yeah. right. So this is the PDF version, which means you don't get to see all my amazing animations. And I don't have presenter notes, so see how this goes. But thank you for the vodka. All right, so as I mentioned, we have this sample XPC application. And what we're going to do is we're going to break out the components into separate processes so that we can make it more secure and more robust. So as I mentioned, normally when we'd write this application, we would do the download, the execute, the unzipping all in one process. And again, this is not secure. If someone finds a vulnerability, might exploit our application or crash it. So if we break these into separate components, separate logical components, you can see that we can break out the download component and then the unzip component into their separate XPC services. So the download component, we can then put a sandbox around this using capabilities of the OS. For example, it does need to talk to the network, obviously, because it needs to download traffic and the images, but it does not need to talk to the file system. Even more securely, the unzip XPC service does not need to talk to the network or to the file system. All the unzipping can be done in memory. So again, this means if an attacker finds a vulnerability in the unzip component and gets arbitrary code execution, they're going to be in a very constrained environment. If they're trying to persist some malware or talk to a command and control server, the operating system is not going to allow them because the unzip service is not allowed to talk to the network or to the file system. So they're going to have to find a separate sandbox escape. So conceptually, how does this all work? Well, you have your application, often referred to as the client, and then you have your XPC service. You can almost think of this as a server. And then the two communicate via messages. So the application will send a message to its XPC components and say, hey, do some task for me, or hey, I want to invoke a remote method. Now, the XPC messages are sent as mock messages, which is a low-level message passing capability of OS X. And again, if you want more information about this, Ian's talk go into this in great details. So again, they make the request, make a connection, send requests, and then the remote XPC component will handle that, optionally authenticate, and then send back a response. So if you have an application and you want to break it out or create some XPC components, how do you do this? Well, it's pretty easy. If you're in Xcode, which is Apple's IDE, you basically add a new target and you select XPC service. This will create all the files necessary, and when you compile this, it'll compile it as a separate executable, but still bundle it all up in the application so that it's easy to distribute. Now, one thing to notice is the bundle identifier, and I have that circled. As we'll see later, this is basically a string that the client, the application, can use to find the XPC service. If you think about this again in terms of a traditional client-server networking model, you can think of this bundle identifier kind of as the URL. Again, it's how the client finds the XPC service. So how does an XPC service listen for clients? Well, it does a few things. So first you call NSXPC listener service listener, and you set then a delegate or a callback object, and then you call resume. Then whenever a client connects, since you've set this callback object, the operating system will automatically call the listen should accept new connection method. And this allows the server to examine the client and say, hey, is this someone I want to be talking to? If the client is okay and the server says fine, then the connection is established. Again, this is similar to kind of bind, listen, accept in the traditional client-server networking model. So then the XPC service has to obviously implement some functionality that the application can use. So again, going back to our downloader application, we can just implement a download function. Let's call it download image. And here you can see this is code in Objective-C, how you go and download code. So again, this is implemented in the remote XPC service. It's now external to the application. All right, so now back to the application, the client. How do we connect and talk and utilize this XPC service component? Well, the first thing we do is we make the connection. Again, this is kind of similar to connecting to a server on the internet, but again, it's a local process on your box. And you do that with the init with service name, and you give it then that bundle identifier that I mentioned earlier. And then the operating system will use this bundle identifier and go out and find the XPC service. The XPC service will be able to examine the client, and if it's happy with the client and authenticate it, the client will then be connected. Once you've connected, you have an access to the XPC service, and you can invoke remote methods and call its functionality. All right, so that was XPC basics. Let's now talk about Rootpipe, which is an XPC-based privilege escalation vulnerability. So the bug itself is interesting, and we'll get into its details, but the timeline itself is also, to me, even more interesting. So we can see in the middle there, October of last year, Emil publicly discovered this vulnerability and submitted it to Apple. Took them about 6 months to patch it. Their initial patch was insufficient, as we'll talk about. But if we look before that, we can actually see that there was a piece of malware that, as I mentioned, exploited it as a 0-day. So I believe it was separately discovered by other adversaries, and they were bundling it in their malware to do some malicious activities. And if we look even further back, if we look at the disassembly of the code for OS X, the very initial introduction in 2010, it looks like this vulnerable code was in there in the inception of OS X. So this means from the very beginning of the introduction of OS X, this vulnerability may have existed, so 10, 15 years ago. So let's look at the actual vulnerability. So OS X has this private XPC service that's called writeconfig, and we're going to be talking about this a lot. The writeconfig XPC service exposes a lot of remote methods, and one of these methods is the create file with contents. Now, if we look at the disassembly, we can see that basically what it's doing is creating a file. And you're like, all right, why is this a problem? Well, it turns out that anyone can connect to this XPC service. There's no authentication, so guest users, admins, anyone in the box can talk to this undocumented private XPC service and invoke this method. And this method allows you to specify the path, the content, and the attributes of the file that you're creating. And since this writeconfig XPC service runs at root, this means you can obviously very trivially privilege escalate. So, for example, what we can do is we can talk to the XPC writeconfig service. We can say, hey, here's a copy of a shell. Please create it, say in the temp directory, and please set it to be owned by root and have the setuid bit set. And then the writeconfig XPC service will be like, sure, no problem. I'll do that, and now you have a nice shell that when you execute will give you a root prompt. Really doesn't get much easier than that. So let's dive into a little bit deeper all of those steps, talk about how we can connect to the XPC service, what parameters we have to send, kind of fully understand the vulnerability at a low-level detail. So the first thing we want to do is to be able to connect to this undocumented writeconfig XPC service. So we could do that directly using the low-level XPC methods I talked about earlier, but it turns out there's an easier way. There's actually another private undocumented object called the writeconfig client that exists in the system administration framework. And this was actually designed by Apple to talk to the writeconfig XPC framework, XPC server component. So we can utilize that. It's kind of an extra layer of abstraction, but takes care of all the details. So what we can do is we get a copy of this from the system administration framework, and then we call the writeconfig client shared client method. And this gives us back a singleton instance of the writeconfig client object that we can then use. So now that we have this object, we can authenticate and connect to the writeconfig XPC service. If you look at the disassembly, you can see the writeconfig client calling or invoking some of the low-level XPC methods we talked about earlier. So you can see there's that ns-xpc-alloc. We can see that there's the init with service name. So under the hood, this code that's in this shared framework is going to be connecting to the writeconfig XPC server. Now, one thing I want to point out, if we look what's highlighted in red on the slide, we can see that this method takes an object, which is supposed to be an authentication object. Well, it turns out if we pass this nil as a parameter, this allows anyone to authenticate. So in Objective-C, nil is not necessarily the same thing. It's actually not the same thing as a null pointer. So you can actually send messages to a nil object, and they just kind of get absorbed by the ether. So this is part of the vulnerability that you can basically anyone can authenticate to this function. All right, so now we're connected. In order to talk to it, we need to get a copy of the dispatch object, which is basically one more level of abstraction. So what we can do is the writeconfig client has a method called remote proxy. If we invoke this, this gives us a dispatcher object, which then we can send message requests to that will then be propagated to the remote writeconfig XPC service. So again, it's just a way for us to talk or send messages to the writeconfig XPC service. So we call this, and then this gives us back a writeconfig one-way dispatcher object. So it's just a dispatcher object. Then step 4, we now have this dispatcher object, and now we can send methods to the writeconfig XPC service, which is running as root. So what we do is we call the create file at path method. Under the hood, this goes into a little more details. It adds something to the selector. But the end result is our message, our request, will be sent to the remote writeconfig XPC service, and that will create the file for us. So we can combine these into an exploit and do the 4 steps. So first thing, again, we do is we get an instance to the writeconfig client object. We then authenticate to the remote writeconfig XPC service. We get an instance of the dispatch object, which then allows us in step 4 to finally send the message to the writeconfig XPC service and say, hey, please create a file for us, and by the way, it's a shell, and please create it as root, and please set the SUID bit. So if we monitor this with a file monitor tool, such as fsusage, when we execute the exploit, we can see exactly what's going on. So first we can see the Rootpipe executable, that's just our local exploit, loads bin/ksh into memory. It then sends that over, and then we look and we can see the writeconfig process. This is, again, the remote XPC service that's running as root. We can see it's creating a temporary file that we call myshell. Again, we can specify exactly where and what this name is. And then you can see it chmodding and choning it so that it is owned by root and has the setuid bit. So again, when we execute this shell, which the writeconfig service has just created for us, we will be happily root. Now, there's one thing about older versions I want to mention, and that is they were still vulnerable, but it turns out that guest users could not exploit them. So on recent versions of OS X, you could pass a nil object to the function, authentication function. On older versions, this failed for some reason. I'm not sure exactly why, but you have to actually pass an authentication object. Turns out this isn't actually too bad because default users on OS X are admins, so they can create this authentication object without having to create or ask for a username or password prompt. So it's still pretty powerful. All right, so let's talk about someone who already knew this and was actually exploiting it as a 0-day within some malware. So the malware was named, or is named, XSLCMD. It was submitted to Virus Bulletin, I believe, in August of 2014, and it wasn't flagged by any AVs at the time because it was a custom new piece of malware. And then about 3 or 4 months later, FireEye did some more analysis on it and detected that, hey, this is a new piece of malware, and it wrote an extensive report on it. Now, in their report, they articulated all the features. They said, hey, it's a fairly standard OS X backdoor. It's got the ability to allow the attacker to have a reverse shell, do screen capture, key logging. So they did a pretty good job. But there was no mention of any privilege escalation exploits in the malware. So fast forward a little bit. Emil found this bug, reported it to Apple privately, and then Apple took about 6 months to patch it. When Apple patched the vulnerability, Emil wrote a nice blog detailing how he found the vulnerability and kind of exactly what the vulnerability was. So someone took this information, kind of was, I guess, scanning older pieces of malware. It turns out that they found out that this copy of the XSLCMD malware actually contained this vulnerability. So I wonder, why didn't FireEye mention it in this report? My theory is, they just missed it. Probably not something malicious there. So if we look at what the malware was doing, how it utilized this exploit to figure out what it was doing, we can look at the disassembly. Now, turns out, I mentioned the malware does key logging. On OS X, user mode code can capture key presses. But in order to do this, the enable access for assistive devices has to be checked or enabled. Now, you can enable this through the UI, but when you do that, it prompts you for a username and password. And if you try to do it programmatically, again, you have to be root in order to enable this. But once enabled, you can keylog to your heart's content. So if we look at the disassembly for the malware, we can see what it's doing. Now, in the UI, when you click that enable access for assistive devices, all this does is it creates a file called .accessibilityAPI-enabled that's in the var/db directory, which is owned by root. And this file just contains a single character, the letter A. So it's pretty much a marker file. The operating system says, hey, if this file is created, I'm going to allow user mode code to capture key presses, because it assumes that you had to be root to either create this file programmatically, or if you did it via the UI, you would have gotten an authentication prompt and would have had to put in the user and password. So if we look at the disassembly for the malware, we can see it's actually exploiting the Rootpipe vulnerability to create that marker file which enables keylogging. So basically, again, the malware was using this exploit before it was publicly known, before Emil had found it, before it was reported to Apple, in order to enable keylogging once they infected a target system. All right, so now let's talk about Apple's response. They took about 6 months to initially patch it. And then I'll talk about how their patch was flawed, and then ultimately how their second patch looks a little better. So the first fail, in my opinion, is they decided not to patch older versions of the operating system. Basically, they said, oh, this is too much work. Turns out, it's not that much work. And Pedro actually released some code that would monitor client connections and block ones that weren't authenticated on older versions. So, it's kind of sad or funny, probably more sad, that when security researchers without source code are able to provide a patch, even when the vendor isn't. So again, in my opinion, this was kind of a misstep on Apple's part. All right, so what did Apple's patch do? Well, as the diagram shows, they did not modify the writeconfig XPC service. Instead, they simply added an authentication mechanism. So I mentioned earlier that anyone could authenticate. The analogy I like to use is that this writeconfig is kind of like this exclusive club you want to get in. And once you're in, you can do whatever you want. So what they did was they added a security guard at the door that basically is now checking badges to not allow anyone in. So before they didn't have a security guard, anyone that walked into the club could get in and then get root. So what this security guard does, this authentication check, is validate the client that's trying to connect. And if the client is an Apple executable, it will allow it to connect and perform whatever task it wants, including creating these files as root. However, if it's an unsigned, arbitrary, for example, hacker executable, the security guard or the authentication mechanism is going to block it and drop it on the floor. So if you look in a little more details, we can figure out exactly what they're doing. So as I mentioned, anytime a client connects to an XPC service, the operating system will automatically call the listener should accept new connection method. And then this allows the server, the service, to examine the client and see what's going on. So what Apple did is that's exactly what they did. They added some code, some logic in this method. And what they do is they look to ensure that whoever's connected is trusted. And the way they do it is by looking for an entitlement, which was the com.apple.private.admin writeconfig client. And if the client connecting to the XPC service has this entitlement, they will be allowed in. Otherwise, they won't be allowed to connect to the XPC service, which means they won't be able to utilize the remote methods. So again, this is the disassembly for the listener should accept new connection. Again, this is Apple's first patch. We can see that whenever a client connects, what the code does is it grabs the client's authentication token and then checks the entitlement to see if it matches the one they're looking for. So what are entitlements? Well, entitlements basically confer specific capabilities or security permissions. They're basically a blob that's embedded in the digital signature of the binary. And again, to think of an analogy, I think of it as you having an ID, and then on the back it has certain capabilities. So in the US, you can get a driver's license, you flip it over, it'll say you're allowed to drive passenger cars, but you can take extra tests, and it can say you can also drive an 18-wheeler. So you can kind of think of this, again, just extra checks or extra capabilities that you can have. So what they're looking for here is for binaries that are signed by Apple that have the com.apple.private admin writeconfig client. So I looked at this and I was like, yeah, I see what they're doing. I kind of understand. But in my opinion, they didn't actually address the issue. And the issue, in my opinion, is that this writeconfig XPC service will create files as root without asking for a username and password. They didn't change that. They just put this security guard in front of it. So if we can thwart the security guard or bypass in some way, game over. Once we authenticate, we can re-trigger the exploit, re-trigger the vulnerability, and get root, even on a fully patched system. So I was flying back from immunity. I live in Hawaii, so it's a really long flight. So I decided to poke around at Apple's patch, and I found a weakness, which I'll talk about. So here's a video that, I guess it's a PDF, so you can't see the video. But basically what my video does, it just showed that I was able to successfully exploit that. And I'll talk about exactly how I was able to do that. So again, the goal was simply to reconnect to the XPC service. Again, this is because they didn't change the code in the XPC service, they just changed and added an authentication. So if we can authenticate and reconnect, we're good. We can re-exploit this vulnerability. Now, I mentioned that this authentication is done on this entitlement. So I figured if there was some way to trick or coerce or somehow gain this entitlement, we would be able to reconnect and re-exploit. So I want to talk about all the things that I tried, and one of them eventually succeeded. And I think it's important to talk about what failed and also what succeeded. I go to a lot of security conferences, hear a lot of really smart people talk, but a lot of times they just present what worked. And maybe they're way smarter than me and always get it right the first time, but for me, I try a lot of things that fail, and then sometimes I get lucky and it works. So I'm going to talk about trying to fake the entitlements, trying to infect entitled binaries, talk about injecting into these entitled trusted processes, some hijacking, and then ultimately some processes that loaded plugins. So the first thing I did was try to fake this entitlement. remember that when you try to connect the XPC service, the security guard says, hey, before I'm going to let you in, I'm going to check that you have this com.apple.private.admin writeconfig client. So I said, can I create my own executable and just add that entitlement, and then, will it let me in? So I went in Xcode, and you have an entitlements file, and you're free to add whatever you want there. So I added that entitlement, compiled, everything was happy. But then when I ran it, the operating system was like, get out of here, and blocked me and killed my process. So again, thinking the security guard, I showed up with my ID and said, hey, I'm really allowed to do this capability. But the security guard was like, yeah, you say that, but this is obviously a fake ID. I'm not going to let you in. So this did not work. So I was unable to fake the entitlement. So what this means, or what this meant to me, was that I had to somehow figure out a way to abuse legitimately entitled binaries in some way. Basically, coerce them to load some malicious code or exploit one of them in a specific way. Because again, the authentication check is only done at the process level. So if you can get a malicious dilib loaded into the process context of one of these trusted entitled processes, when you connect to that XPC service, it's just going to look at the process as a whole. It doesn't say your dilib is unsigned. It says, no, this is an entitled process, and let you through. So I first had to find a list of all the entitled processes. So I wrote a simple Python script, just ran through the entire file system, and looked for any processes that had the com.apple.private.writeconfig entitlement. Turns out there's about 50 or so. So that kind of gave me a good start. So now I had this list of 50 executables that could talk to the writeconfig service, and I just had to figure out a way to exploit them. So the first thing I tried was to infect them. Said, hey, is there a way if I add a new dependency, hijack the entry point, add my own code, will this execute and run? Well, it turns out that the OS loader, DYLD, actually, and the kernel, verifies the digital signature of any binary that you execute. So if you modify it, it's going to detect that you've tried to infect it and kill the process. Now, on OS 10, you can actually run unsigned code. So I thought maybe I would try to remove the digital signature, so then the loader wouldn't check the signature. But it turns out, as I mentioned, that these entitlements are embedded in the digital signature. So if you remove the digital signature, yes, the executable will be able to run, but you've also lost the entitlement. And remember, we have to have that entitlement. So this failed as well. I then tried to do some load time injection. I said, hey, if I can get a trusted application, an entitled application, to load a dynamic library, I will be able to talk to the XPC service and re-exploit the vulnerability. So on OS 10, there's an environment variable called dyld insert libraries. And what you do is you give it a path to a dilib and then an application. And the loader will load your dynamic library into the process space as it starts the application. This is very similar to LD preload on Linux. So I tried this, and this failed. And the reason this failed, if we look at the source code for the loader, dyld, we can see it iterates through all the environment variables. And if the process is restricted, which means it's either SUID or it has entitlements, it actually prunes out or ignores the environment variables. So the method is called prune environment variables. And we can see, like I said, it's going through and it sees any environment variable that starts with dyld. It just chops it off and ignores it. So this means that even if you specify that dyld insert library environment variable, the loader is going to be like, hey, this is an entitled binary, and ignore that environment variable. So your dilib never even gets loaded. So this failed as well. The next thing I did was try dilib hijacking. And I'm going to briefly talk about dilib hijacking because it's kind of a newer attack that I think is kind of cool. So dilib hijacking is conceptually very similar, if not identical, to DLL hijacking on Windows. Basically, you can find vulnerable applications that have either of two scenarios, which I'll talk about, that you can then plant or place a malicious dilib that will get loaded automatically by the loader when the application is run. So the first scenario is if the application has a weak dependency that's not filled. So at the top, we have this executable, and it says, hey, I have a dependency on blah.dilib. The loader is going to look for that, blah.dilib. Now, if it doesn't find that, because it's a weak dependency, it's just going to be like, hey, I didn't find your dilib, and the application's like, that's no problem. It was a weak dependency. If it was there, I was going to use it, but since it's not there, no worries. So what a malicious hacker can do is plant or place a dilib with the same name in that directory, and then whenever that application is run, the dilib, even though it's unsigned or malicious, will get loaded by the loader automatically, and then be running in the process or the application. So the second scenario that you can hijack an application is if an application has several run paths that it specifies, and that the dilib that it specifies is not in the primary search directory. So I think the picture describes this better than I'm able to explain. But again, see we have an executable, and it's looking for a dynamic library, again, called blah.dilib. Now, there's certain load commands that can tell the loader, hey, I have this dependency, but I'm not sure exactly where the dilib is. So here's several directories. Please go look for it in these directories. And I know one of these directories has the dilib, but I'm not sure which one it is. So the problem arises if the legitimate dilib that the application needs exists in a secondary directory, because this means that the loader is first going to look in another location first. And again, what a malicious adversary can do is plant a malicious dilib in that primary search location, and the loader will naively and blindly find and load that. So again, then your malicious dilib will be loaded in the process context of an application. So this ultimately failed as well because you can't target arbitrary applications. You have to have applications that are vulnerable to a dilib hijack. So either have a weak dependency or look in multiple locations and not have this dynamic library exist in the primary search location. So I scanned all the binaries on the file system, and there's a ton of applications that are vulnerable to dilib hijacking, but none of them are entitled. So there was no union between basically the list of trusted executables and the ones that were vulnerable. So we could not use dilib hijacking in order to re-exploit this vulnerability. So I didn't give up hope. The next thing I tried was runtime injection. I said, okay, I'm going to start one of these trusted entitled applications and then just try to inject code into it. And if I can inject code into these applications, that injected code can talk to the right XPC service and re-trigger the vulnerability. So the way you do code injection on OS X is pretty similar to Windows, at least conceptually. So the first thing you do is you get access to the remote process, and then once you do that, you allocate memory for your remote stack and your remote shellcode. Then you copy in your shellcode. Then you change the memory permissions, and then finally you initialize and start a remote thread at the location where your shellcode. So again, this is pretty standard stuff. Problem is, at least for attacker, is that in order to get access to a remote process, you have to call task for PID. This is kind of like giving you permission to remotely allocate memory, start remote threads, control the process. Turns out on OS X, at least in recent versions, you have to be root to do this, even if you own the process that is running. So again, we don't have root. We're trying to get root. Since we don't have root, we can't even get access to the remote process to inject our code in. So this fails as well. So the last thing I tried, which was ultimately successful, is I looked for these trusted and entitled applications and said, hey, do any of them load plugins? And I found one called the directory utility, which, if we see, we dump its entitlement, has the correct entitlement. And also, inside its application bundle, it has a directory called plugins. So I was like, yeah, this is promising. So I said, does this load plugins? What is this doing? There's this folder called plugins, and it has some dynamic libraries in there, kind of what's going on. So I disassembled that, and there's a method called load plugins. And if we run, again, a file monitoring tool, such as fsusage, we can see, yes, it's iterating through this plugin directory. And every bundle, all the dilibs that are in there, it loads into its process space. So I said, hey, can I install an evil plugin? And will this process, this entitled, this trusted process, then be coerced into loading it? So the problem is that the directory utility lives in system and is owned by root. So you actually have to already be root in order to put a file into its application bundle. But let's forget that for a moment, because I wanted to test, would it even load a malicious plugin, one that was unsigned. So what I did was I authenticated, and then I copied just a malicious unsigned dynamic library into that plugin folder, and then re-executed the directory utility. And in the bottom, you can see that, yes, indeed, the directory utility application loaded my malicious unsigned plugin into its address space. So we're close, but not really, because we had to authenticate in order to copy our malicious plugin into the directory utility's application bundle, because that application is owned by root. But if we could change the ownership of that application, be game over, because it's entitled and it does load our plugin, even though it's unsigned. So it turns out we can change the permissions of that directory utilities. Actually, really, really easily. If you copy the directory utility application into the temp directory, the ownership is changed from root to the current user. So we can see it is now owned as Patrick. So now I can copy my malicious plugin into the plugin folder, even though it's unsigned. And then when I execute the directory utility, we can see the diagram. This is exactly what happened. Execute the directory utility goes through all its plugins. It loads my unsigned malicious plugin. My malicious unsigned plugin says, hey, I want to talk to the writeconfig service. So it goes and connects to that writeconfig service. The security guard says, hey, wait a minute, I'm not allowing anyone through anymore. I'm checking all your IDs. And it says, what process, what task is requesting this? And it goes and looks at the operating system, and it says, oh, the directory utility. It checks the directory utility's entitlements, and lo and behold, it has the necessary entitlements. So it lets my request go through, and then I can create any files again as root. So again, this is how we do it. 3 lines of Python, right? 100% success. This is not a heap corruption, memory vulnerability. So yeah, this is how you do exploitation on OS X. Pretty easy. So again, step 1, we copy the directory utility into the temp directory. This gives us the ability to modify it. We then copy in our malicious plugin, execute it, game over. So Apple patched this finally again. They gave it CVE 2015-6373. And I like this picture because it illustrates the flow control graphs for the authentication mechanisms. We can see the original version did no authentication at all. So again, there was no security guard. Everyone was allowed to come in and request files be created as root. The one in the middle, that's 10.10.3, that is the first patch that Apple created. And we can see there's a bunch of checks, but obviously there weren't enough. And then finally, the second patch where they addressed the vulnerability I found, you can see they added tons more checks. So, this shows that if you're going to do security, you really have to think about it and think about those corner cases and what exactly you're doing. So let's briefly now look at Apple's second patch and figure out what they did to mitigate this attack. So what they did was pretty easy. They basically said clients have to live in /system or /user, but not /user/local. Now, since /system and /user are both owned by root, this should generically thwart the attack, and it did, and others as well, because obviously you can't move files out and stuff, and obviously you can't copy in files, for example, to exploit or coerce these trusted executables, because you need root in order to touch or modify anything in system or user. A little more comprehensively, this is what the patch did fully. So the other thing they did was they also added some new entitlements, and this just gives them more fine-grained control and allows them to limit how many processes can talk to that writeconfig service. However, the quote at the bottom that Pedro tweeted about I think is very insightful, because again, Apple didn't really address the core issue. That writeconfig service is still there, and it has a remote method that will create any file for you anywhere on the system with any privileges, assuming you can authenticate. So the problem is, and I'll just read this quote, is the problem of their fix is that there are at least 50 or so binaries using it, and a single exploit in one of them and the system is owned again because there's no fundamental fix inside a writeconfig. So I think their patch for now is decent, but I really wouldn't be that surprised, because if anyone finds any way to coerce or exploit these 50 or so entitled binaries, it's just game over once again. Unfortunately, we've seen Apple kind of do this with patches. They very narrowly patch things. I've done some work with Gatekeeper where I found a vulnerability, talked to Apple, and they patched just the one specific code patch. And I'm like, serious? Because I can just use this other code path and re-exploit the same thing. So that's just a good thing to remember. All right, so we saw that Apple contained, OS X contained trivial to exploit privilege escalation vulnerability from its very beginning. Some malware writers, probably the Chinese, found it and were exploiting it. Apple's initial patch was broken. So, these things bother me, right? I love my Mac, but it's kind of really easy to hack. So I briefly want to talk about some ideas about how we can keep our Mac secure. So my hobby, kind of on the side, I have a small OS X security website, and I have some tools and some malware I briefly want to talk about. So first, there's a lot of modern OS X malware samples that you can download and play with, including the one XSL CMD that contains the privilege escalation vulnerability. AV guys don't really like to share, so it took me a while to get this, but I figured, sharing is caring. More importantly, I wrote a bunch of security tools that I run to protect my Mac, and then I figured I should share them as well to make our Macs more secure. So the first tool I wrote is called Knock Knock. Now, knock knock has a simple job. When I say knock knock, it should tell me who's there. In other words, it should tell me everything that's persistently installed on my Mac computer, everything that's set to automatically execute when I return on my Mac or log in. It's kind of like auto runs, but for OS X. The coolest feature, in my opinion, of knock knock is that it has built-in virus total integration. Knock knock itself doesn't differentiate between malware. It's kind of malware agnostic. It lists all your kernel extensions, your launch agents, your daemons, your cron jobs, but it doesn't actually say if one is malware or not. However, when it's integrated with the virus total, it can determine if something is known malware. It can tell you if it's not flagged currently, or it can tell you if it's never been seen before, which might be interesting because normally virus total has a pretty good corpus of files. You can also submit files to virus total, rescan them, and get back the results. So this is a nice tool. One limitation is the fact that you have to run it manually. So it doesn't provide real-time protection. So I wanted something that was a little more proactive as opposed to reactive. So the next tool I wrote is called block. Really creative with these names, I know. Block is pretty much a firewall for persistence locations. So what it does is it actually monitors continually the locations that knock knock reports on. So if anything touches the file system in these locations, for example, tries to install a new kernel extension, create a new cron job, create a new launch agent, launch daemon, you'll get this little pop-up that says, hey, process XYZ is trying to create this new launch agent. Because we don't have animations, this is kind of overlaid, but in the background is hacking team's persistent OS X implant. It persists as a launch daemon. So this means basically if you had block running and hacking team came after you, you would get a pop-up, a warning saying that someone was trying to persistently install a launch agent. On top of this is another piece of malware, exploited another zero-day vulnerability, one that Stefan Esser reported. He didn't do it very responsibly, so the malware authors were able to utilize it. Block didn't detect the exploit, but when the exploit payload, even though it was running as root, went to persistent malware component, Block detected it and would protect you. So again, not bad for a free tool. And then finally, the last tool is Task Explorer. This is kind of just like Activity Monitor, but better. So it lists all your running processes, but it tells you a lot of cool things about it. Shows you what's signed and who it's signed by. Again, it has virus total integration. And then when you click on a task at the top and the bottom, you can see what dynamic libraries are loaded, what files it has open, and what network connections it has. It also has a global search, so you can say things like, show me everything that's loaded that's unsigned. So you can see all the tasks that are unsigned, any dynamic libraries that are unsigned. You can also say, show me all the listening network connections. So this is a tool I use a lot when I'm poking around in my operating system, or when I'm doing bug hunting. For example, when I'm trying to see if a process will load an unsigned dynamic library, this is what I use. All right, so just to wrap everything up, hopefully I've made the point, and you agreed, that OS X security is rather lame. So one solution to this, while Apple kind of gets their act together, is for us to audit things. So let's look at these XPC interfaces, right? The writeconfig XPC interface was originally exposed to everyone. Granted, it was private and undocumented, so maybe Apple just assumed no one was going to look at it. But attackers were, right? The malware they created, they found this and were able to exploit it. So again, it's also good. Let's analyze and audit the malware. I don't want to really pick on FireEye, but they did an analysis of this malware, and they didn't report or find the fact that it exploited a zero-day vulnerability. So again, good idea to look at malware to see what it's doing. And then finally, let's audit the patches that Apples are pushing out. I've seen several instances, as I mentioned, where the patch that Apple has pushed out, yes, it closes the specific code path that the researcher or the malware or the hacker was exploiting, but a lot of times the patch doesn't comprehensively address the core underlying problem. So if we reverse engineer and audit them, a lot of times we can find out that the patch itself was not valid, not secure, and hopefully then we can help Apple create better patches so us as Mac users can ultimately be more secure. All right, so that's a wrap. My email address is patrick@synac.com. I'm on Twitter. You can download a copy of the slides. I know they're a little hard to read because of the PDF, so you can kind of get all the details and that. And then, yeah, Objective-C is my separate little side hobby. It's got some free OS X tools that might be useful to securing your Mac. So I have no idea how much time we have or not, but I think we have a few minutes or so for questions.
¿Preguntas? Hola, hola.
I'll also be at Synac's booth, so if you want to come and just talk story or talk about that, I will be there as well.
Bueno, muchas gracias. Entonces,
Thank you.
thank you, Patrick.